Hi, in the previous video, we looked at a particular circuit and we tried to derive the input output relationship for it. And then we compared it, if you remember, with the low pass characteristic that is shown here, right? Now, I just wanted to introduce these characteristics, and I'm not really going to give a proof of it, but if you want, you could plot these curves on MATLAB, let's say, for different values of k, f naught, and q, and look at the curves and see that you get what I have, uh, that this equation actually represents a low pass filter, and this equation represents a high pass filter, and this equation represents a band pass filter. One way in which I think you can see that is by just looking at what happens as increases and becomes a very big value, or f becomes almost equal to zero, and see what happens to the gains that are given here. Okay, so I'll leave you with this. But what I wanted to discuss next is just the low pass filter characteristic and its relationship to Q. Okay, so here are different low pass filter characteristics, and these are all second order filter characteristics, but they are plotted for different values of Q. Okay, so you can see that so for a very low Q, take a look at this filter. It's very slowly changing, right? And you have a characteristic like this, which is kind of monotonous in the sense that it's always decreasing. For Q equal to 0.5 as well, you have that. But as you go above Q equal to 0.707, which is 1 over square root 2, what you start to get is you start to get a ripple in your filter response. Okay, so for example, you have a ripple here. So your response is no longer just straight and then going down, but it just goes and then there's a small ripple before it starts to fall down. But what you can see is in these filters where you have this ripple, the fall down is also faster, right? So you have a constant gain. Let's say this, let's take this black trace here. So you have a constant gain till approximately here, and then the curve falls down quite rapidly. While if you are on less than, while let's take as an extreme example, this q equal to 0.1, you can see that this transition region is very large. Okay, so as q increases, your transition region becomes smaller, but you start getting ripple in your filter, and that kind of gives us a compromise between the two characteristics, right? And we can get two kinds of filters. Ideally, we would like the filter to have a constant gain in the pass band, a zero transition region, and a constant gain in the stop band. We can't get that. So what we can do is we can allow for a ripple in the pass band, and allowing for a ripple in the pass band gives us a smaller transition region, and we reach the stop band quicker. But if you say, well, no, I don't want any ripple in my pass band, I don't want the gain in my pass band to vary, then you have another kind of filter where you don't have any ripple, but then the transition region is much faster, much larger, right? So these kinds of filters which do not have a ripple in the passband are called Butterworth filters, while the filters that allow for a ripple in the passband and have a faster transition region are called Chebyshev filters. And these two filters can be built by changing the Q, right? The quality factor. And the conditions are written here. For a Chebyshev filter, the quality factor is greater than 0.07. Okay. And for a Butterworth filter, I've done something wrong here. This should be less than. So the Q is less than 1 over square root 2. So if you have this, you get a Butterworth filter. And if you have this condition, you get a Chebyshev filter. Hope that makes sense.